Thermometer, and instead of looking inward, we're going to be looking outwards towards space. And as was previously mentioned, my name is Bridgette Davey, and I am something known as a Lucy Ambassador. So how you might have heard of ambassadors before is an ambassador for a country. Well, instead today, I'm going to be coming to use an ambassador not for a country, but for NASA. And in addition to that, for the Lucy mission. So please join me on an epic journey to the fossils of our solar system. So when you hear the word solar system, you probably think of the planets: Earth, Mercury, Venus, Mars, Saturn, Uranus, Neptune. However, it's a solar system. So in addition to these planets, there are many other bodies out there. And some of these stellar bodies are known as asteroids. And asteroids vary in a large range of sizes. So most of you guys drove here in a car today. Some of the asteroids that are in space are the size of a car. However, some of them are even larger than that, and there's even some asteroids that are the size of a huge mountain. And the reason why these asteroids are interesting is because they act as fossils of the early solar system. And they can tell us the story of how our planetary neighborhood came to be. So a good analogy to think of is that fossils are to dinosaurs as asteroids are to the solar system. So NASA is going to be sending a mission to a never-before-explored group of these planetary fossils that are known as the Trojan Asteroids. And the mission is called the Lucy mission. And the reason for that is that it's named after an early hominoid fossil found known as the Lucy fossil. And this was found in Ethiopia in 1964. So these Trojan asteroids are out beyond the main belt of our asteroids, and they orbit along with Jupiter. And there's two different groups of them. There's the leading swarm, and then there's the trailing swarm. And so why are these Trojan asteroids even interesting to us? As I stated before, they act as the fossils of the solar system. So early on in our solar system's life, there's a giant disk of different materials that was rotating around our sun when it was first being formed. And inside of these disks was a bunch of different materials. Many of them, there's like globs of different elements, there's rocks, there's ice, and because it was spinning very, very fast, it was really volatile. And so these materials would start to bump and collide with one another, and I like to call them sticky clicks. They would click against one another, and then they would stick. And as these materials were starting to stick together, they would get bigger and bigger and bigger, and it would be similar to a snowball. They would start to get a bunch more gravity, and then they would be grabbing all these gases that were around it, and then they would slowly start to form atmospheres. And then over the time span of millions of years, we got the 4 inner rocky planets we have now, which Earth is a part of, and then the 4 giant planets, many of which have gas atmospheres. So as this was going on, and these things are violently smashing together, bits are splintering off, and the planets are forming, we are interested in how that began to happen. And so what we want to do, what NASA wants to do, is look at these planets and get more information about how they formed and about some of the materials that make them up. Only we have one major problem. Remember how earlier I talked about how they're growing and they're starting to get gravity and there's atmospheres that are forming on them? Well, as all this is happening, they're being exposed to extreme heat and extreme pressure. And as you know, if you stick a metal pot in the microwave and it becomes really hot and under a lot of pressure, it gets warped. And so the same thing happens to these planets. And so even if we were somehow able to scoop beneath the gas atmospheres of them and investigate them, these building blocks or these sticking clicks that had formed them would be so altered by this heat and pressure that it would tell us basically nothing. Which is the reason why we're so interested in these asteroids, because not all of those little bits and blocks that were in that disk ended up forming planets. Some of them formed these asteroids. And so these asteroids are not altered by this heat and pressure, so they can give us information about what our early solar system might have looked like. Now, there's 3 main questions that Lucy's data is going to help scientists start to learn about. The first one is what sort of rocky and icy materials actually make up these planets. The second one is how and where did these planets form? Did they move around in the solar system? Did some of them end up in different orbits than they are now? And then finally, how did the materials needed for life make it to Earth? So again, all of these materials came from the same disk, and so we want to know, like, how did carbon get here? How did hydrogen get here? How did oxygen get here? And so these asteroids can help answer some of these questions. So again, NASA is going on a road trip to a record-breaking number of asteroids. They're going to be visiting 7 asteroids total. One of them is a main belt asteroid, and then the other 6 are Trojan asteroids. So Lucy is going to be launching from Cape Carnival in the early morning hours of October 2021. It's going to start out in an orbit that's close to that of the Earth's. And as you can see here, the Earth's orbit is in blue, Lucy is right here in red, and then each of these gold dots are the targets that it's going to be trying to reach. So Lucy's actually going to start off by flying by the Earth and relatively close to its orbit. And the reason that it's going to be doing this is it's going to use the gravity of Earth as a sort of slingshot in something called a flyby. It's known as gravity assist. So it's going to be out in Earth's orbit, and it will use Earth's gravity to kind of slingshot it out towards the farther targets that it's trying to reach. This will cut down on the amount of gas and energy that it would otherwise need. So for this first target, it's going to be going towards a main belt asteroid known as the Donald Johanson asteroid. And this asteroid is named after Donald Johanson because he was the one who discovered that earlier fossil that I mentioned, the Lucy fossil. So this asteroid is of particular interest to us because one, it's one of the younger asteroids that we know of, and two, it's actually a remnant of a collision. So it can help give us information about how those building blocks were moving around in that earlier disk. So the next target that Lucy is going to be flying towards is Euripides. Euripides is also a survivor of a collision. However, the reason why Euripides is so interesting is it's theorized that it was actually part of a larger asteroid and then broke apart. And there's also a theory that some of those parts of on the inside of an asteroid got deposited on the surface. So similar to the way how you can cut open a cake, or if you take a pool ball and you smash it against the ground and you can see the insides, this asteroid smashed against another one, and most likely the inner bits of it would have settled on the surface of Euripides. So that can give us information about what the inside of an asteroid would look like. So the next target is Ptolemy. Now, I mentioned previously that these are flyby missions, and what I mean by that is that it's literally just a flyby mission. It's not going to be like the moon landing. The probe isn't actually going to be landing on the asteroid. It's just going to be barely skimming by it. And this is one of actually the main problems for the mission, and it's also going to take a month between each of them. So there's going to be time where it's not actually doing anything, and it's traveling from one point to another. And so it's going to be using cameras to collect most of these data. However, the data is going to be relatively large. It's going to be 1.25 gigabytes, which might not seem that large to you. However, you're going to be sending this across space, which is going to take about a month to travel. So in between how it's visiting each of the asteroids, it'll then be sending all this data back to Earth. And for analogy's sake, 1.25 gigabytes is about an hour's worth of streaming TV. So the final one of the early Trojan the leading swarm that it's going to be visiting is known as Lucas. And Lucas is particularly interesting because of its shape. It's long and elongated, and it has a very weird spin. So it's kind of like if you've ever seen a drunk person out stumbling along. That's what Lucas is like in terms of all the other asteroids. So as I previously mentioned, Lucy is going to be using the Earth's orbit as energy for its gravity assist. It's also going to be using it for course adjustment. When you have a large probe that's out in the vast reaches of space, you can't exactly have a little remote control that controls it. So what it's going to do is it's going to use Earth's gravity in its orbit to actually steer it. So after it's gone by those previous 5 asteroids, the final targets are actually going to be 2 for the price of 1. And that's the Patroclus asteroid and the Menicius asteroid. So these 2 asteroids are what's known as a primordial binary pair. And what that means in English is they're binary, so they're orbiting each other. And primordial just means that they're from the very earliest formations of our solar system. And the reason why they're so valuable is because they're both really near each other. So Lucy can just skim right by them, and it's going to be getting 2 for the price of 1. They're so close that if you stood on Patroclus and we're looking at Menicius, and Menicius would be like the moon, it would appear 10 times larger than our moon currently does. So Lucy's going to be bringing instruments to collect the important info on this trip. Again, as I previously mentioned, it's a flyby mission. It's not actually going to be touching down, which is part of what makes this so difficult, because how are you supposed to get any information about an asteroid if you're just kind of skimming by it? So because of that, many of the instruments that are going to be aboard this mission are all camera-based. And I'm not sure if you can, well, you've obviously noticed, but most of them have an L in front of it. And the reason for that is it's from the Pseudo-French la sound, and that's because all of these instruments have been aboard previous missions. And so we put an L in front of it for Lucy, or Lattez, in order to differentiate between the 2. And earlier on, I mentioned this high-gain antenna, and that's what's going to be sending the data back to Earth. So the high-gain antenna is also going to be able to help us steer. If you think of bats and how they use echolocation, they send out a wave and it bounces back. It's a similar concept to this, only instead the high-gain antenna is going to be using radio waves. And in addition to that, a way to think about how it is going to be sending the data with us, you can think of your TV. So if you have a TV, most of you have some sort of dish outside if you have telecom or something similar. So in this case, the dish is the high-gain antenna, and the TV station is like the spacecraft, and then there's a large radio disk that's back here on Earth that'll receive the data. So the first of these cameras is known as LaLaurie. So LaLaurie is a black and white camera, and it's primarily going to be used to show us what the geological features will look like on all these asteroids. So right here, this is a picture of what the LaLaurie camera on the New Horizons spacecraft saw on Pluto's moon, Charon. So as you can see, this is really good resolution for something that's millions of light years away from us. And you can see a lot of different features on here. There's what looks like a ravine. There's several different craters. And so we'll be able to get similar resolution pictures of these asteroids. And so we can see if there's features that are like mountains on them. We can see if there's craters. And so that's why Lalaurie was picked out for the Trojan Asteroid mission. So the next camera is more of a 2-for-1. It has 2 different cameras inside of it, and it's known as LaRalph. So the first part of it is called the NVIC camera. And instead of being in black and white, this is a color camera. Only this isn't like your ordinary Kodak color camera. This camera has special features inside of it that will allow it to sort of filter out what different types of light are being reflected back. And the reason why that's important is even if you just look around this room, you can see that things are different colors, which means that those objects are going to reflect light differently. And depending on the material of something, like my ring, it's shiny, or the chairs, which are opaque. So depending on the material of something, that's going to affect the way that it reflects light. So the NVIC camera can help tell us about what different sorts of materials make up these asteroids. So the picture that you can see right there on screen is actually of the MU69 Kuiper Belt asteroid. And the reason why this is important is because a Kuiper Belt asteroid is very similar to a Trojan asteroid. So we know that these instruments are most likely going to work for the Trojan mission. So the second part of that camera is known as the Ralph, and that is an infrared spectrometer. So what the Ralph Lisa camera saw on the New Horizons is pictured right here. And the reason why the Ralph is important is because when things reflect things differently in the infrared, that can also give us more information about what materials are making up the asteroid. Specifically, it'll be valuable for looking at different types of ice. So this is what the Ralph Lisa camera saw on the New Horizons when it flew by Pluto's moon, Charon. And it was interested in looking for ammonia ice, which it ended up finding in one of the craters. And so this would again give us information about, for example, how did water end up on Earth? So if we find ice on one of these asteroids, that can give us info about how H2O made its way here. So the final instrument is known as LaTES, and it is an infrared thermometer, and it works remotely. And so the reason why this is important is it can give us info about how these asteroids are going to store heat. So asteroids are out orbiting the sun in addition to Jupiter, and instead of reflecting all of the heat like they might do if they were a reflective surface, they will end up absorbing some of it. And then this heat is given off as infrared radiation. So the LaTES instrument can read the radiation and give us info, again, about the materials in the asteroid based on how they absorb and release heat. A good analogy to think about it is if you're ever on a beach, the sand in some areas is going to be a lot hotter than the cool sidewalk might be. And that's because they're made of different materials and thus absorb heat differently. So finally, while it might be a robot spacecraft that's going on this epic adventure, it's people who are getting us there. And as both of the previous speeches have talked about, there's a wide variety of different people who are in the world, even just looking around in this room. And so similarly, there's a wide variety of people who are part of this mission and helping us get there. As you saw previously on the slideshow, they're like with those solar system, there's artists who are going to be helping, there's people who are helping out with finances. So it's thanks to all these different types of people that we're able to do this. So Lucy's journey will continue. It is launching in 2022. However, it will be out there until 2033, which will be the end of the mission. After this, it will continue to orbit the sun and will hopefully remain in a stable orbit for billions of years. So thank you for coming with me on this epic journey.